Hi. In this video and the follow-up videos, I'm going to go through the main concepts that are involved in magnetism. The magnetism chapter is fairly long and there's a lot of material in it. So I think it'll be helpful if I try to give you an overview so you don't get confused and you can see kind of how the different bits fit together. So I call this the magnetism roadmap. Let's get started. The one thing I want to say about this video, possibly series of videos that I call the roadmap, is that I'm not going to include induction. That's the following chapter, and we're going to come back to that, right? But I'm not going to include this here. I might mention it here and there. And induction is really the key idea of how electric fields interact with magnetic fields, and how changing magnetic fields cause electric fields and currents and so on. So this is really where we get into the realm of electromagnetism, as opposed to separate electrostatics and magnetism. So magnetism, fundamentally, is the following. Moving charges interact with other moving charges, right? And yes, by charge, I don't mean some new kind of magnetic charge. I mean the same electric charge that you know from electrostatics. Right? So, electrons with their minus 1.6 times 10 to the minus 19 coulombs, right? Same thing. Those charges, if you've got two of those charges, right, they're going to interact electrostatically. That is still true. But if they are both moving, and it's crucial, they both have to be moving, then there's going to be a magnetic interaction on top of the electrostatic interaction. That's the key idea. In a way, if you have to put magnetism into one sentence, that would be kind of it, right? Now, the way we do this is via a concept called the magnetic field. Now, when we did electrostatics, we first talked about this charges acting forces on charges, essentially via Coulomb's law, and that worked, well and good. And then we introduced the electric field as a kind of intermediate step. With magnetism, going about it the same way would be really, really difficult, because if you directly try to figure out what is the force on one moving charge on the other, it becomes sort of, I guess you can do it, but it becomes mathematically quite confusing. What direction are the forces and so on. So the way we do this is we're going to go via a field right away. Instead of the electric field, we're going to have the so-called B field, the magnetic field. The B field, I guess, was an A field, and then B field is the second one. But so there's no real reason why it's called the B field. I don't think the B stands for anything, at least not to my knowledge. So in a sense, when you first study magnetism, you're going to meet two different ideas. So part of the chapter, in fact, I think the first part of the chapter is dedicated to what causes magnetic fields. And it's a moving charge, so we can ask if for a single moving charge particle, what kind of magnetic field do I get? If I have a continuous motion of particles, and the prime example would be an electric current, for the wire, right, the charge is constantly running through it, that's going to create a more steady B field, this more steady magnetic field. How do I calculate this? What does it look like? So this is kind of what one side of magnetism is. The other side is then, what do these magnetic fields do? What they do is they cause forces on moving charges, what we said. That can take the form of just a single moving charge, an electron flying by, right, through a magnetic field. What is the force on that electron? Or it could be that we have a whole wire that's carrying current, so a continuous flow of moving charges, so maybe a particle beam, where I shoot, continuously electrons, say. And in both cases, I'm going to get a force on the particle here, or essentially all the particles in the wire that are moving, and therefore on the wire overall. Of course, this one and this one can always be explained in terms of a large number of individual moving particles. Interestingly, this little bit here, that the magnetic fields create forces on current-carrying wires, that's what ultimately underlies the notion of an electric motor, which we're going to look at as an example. Now at this point you might be a bit confused, because you're like, wait a minute, I thought magnetic fields were about like magnets. What about magnets? That's what I've got in purple down here. So these magnets, I think you call a magnet, like a fridge magnet, or a little sort of bar magnet, with like a red and a green end, a north pole and a south pole. Those we call permanent magnets in physics, because they are sort of just there, right? And what about those? So actually we're going to start thinking about those, in part because they are the most sort of hands-on approach to magnetism, and they're also kind of historical, how people first figured out magnetic properties of, say, materials. But ultimately these permanent magnets, like a fridge magnet, can be explained in terms of moving charges. Right? So we'll start out with the idea, hey, there are magnets, they have a north pole and a south pole, and they sort of attract or repel. But ultimately we're able to just explain that in terms of the microscopic structure of these permanent magnets. Right? Initially, though, we're actually going to define our idea of the magnetic field. This sort of intermediate step for calculating forces. We're going to define that just in terms of what it does to magnets, and the prime example would be like compass needle. Right? So initially, we're going to think about, well, how do compass needles, kind of our probe magnet, if you like, the same way we had a probe charge in electrostatics, how does compass needle reacts to different types of magnetic fields? And that's how we're going to define the notion of magnetic field in the first place. Right, by looking at compass needles. Just to get a more intuitive grasp on what those fields are, what they look like. Right, but ultimately they are an intermediate step to figure out the forces on particles. There are a few more things worth mentioning here. One is, if you've got permanent magnets and you play around with them before, you know they don't just attract or repel other magnets, they also attract materials such as iron or other ferromagnetic materials. So iron is the primary one. And we're going to be able to explain that by essentially this picture that ferromagnetic materials, such as like an iron nail, is really made up of lots of tiny magnets on the inside, but they're all mixed up, pointing in all sorts of different directions and aligned. So normally the nail as a whole doesn't act like a magnet. If you bring another magnet near it, those little tiny magnets inside the iron nail align themselves, and we're going to get an overall magnetic effect. Another little side topic is going to be Earth's magnetic field. But really it's just another example of a magnet, although how does it come about? It's actually a fairly complicated question. And if you really want to get into that stuff, I'd suggest you take a course in geophysics. Now one sort of side route that from the magnetic field that I haven't mentioned yet is the thing I wrote down here in green, which is that changing magnetic fields cause electric fields and vice versa. So this is related to this idea of induction. Induction is part of it, and broadly speaking, this interaction between magnetic fields and electric fields, the fact that you can't disentangle one from the other, that is why we have a course on electromagnetism. Right? So why electromagnetism is one word as opposed to electricity and magnetism or electrostatics and magnetism. Right? We won't be able to disentangle them, and we'll see why. And a lot of interesting effects we get from that. Among the ones worth mentioning is, for example, generators. Like pretty much any type of power station that creates electricity for our homes, be it nuclear, wind energy, hydroelectric, you name it. It's ultimately using pretty much the same principle, and that's based on induction. So without induction, never mind that the world wouldn't be what it is in the atomic level, but on a sort of bigger scale, we wouldn't be able to essentially create electricity the way we are. So you wouldn't be able to watch this video. But I won't be talking about this in this particular short video series, because it's going to take us well beyond beyond the introductory level of magnetism, right? But we'll come back to it a little bit later when we talk about induction, once we have a grasp of the basics of magnetism. So this was the very broad overview. I'm now gonna, in the follow-up videos, follow up parts to this. I'm gonna go into some more details, especially about these bits here, and those. And in fact, what I'm going to do next in part 2. So right now you're watching part 1. In part 2, I'm going to talk about permanent magnets, because those are the ones you're probably more familiar with. How do they act? There's some little experiments we can do with them. Then in part 3, I'm going to talk about how moving charges create magnetic fields. These are pieces of math there that we're going to talk about. Although there, again, within that are going to be some topics I'm going to treat in a separate video too. But I'm going to give you the overview of this in a bit more detail than I have just now in part 3. And then in part 4, the last part, I'm going to talk about this side of things, how magnetic fields cause forces, create forces on moving charges and currents. And I'm going to mention some interesting effects we get based on that. Alright, that's it. I want to keep this video short so they're more watchable. So this was part 1. I just outlined part 2, 3, and 4. So I'll see you in part 2 in a minute.